Stereochemistry, and first thing before we start, we're going to go over words, like the definitions of things, how to figure out if something's chiral or not, figure out what kind of chiral center it has, then use all that together. Right? The only thing I will not go over, I told a lot of people this already, I think I will not go over is during this video or just a review session, I will not go over enantiomeric excess observed and like the observed calculations, stuff like that. The last half of the drill module. Right? You have a lot of examples of that in your slides, the textbook, and you've done some in lab. This question I can't make up on my own. So follow your slides in terms of how to calculate enantiomeric excess and figure out how much R and S are in a compound based off the numbers. Right? If you have any questions in that, go ahead and just email me and I can try to explain where you might have gone wrong during your own work, but that's the one thing I will not go over today. Apologize for that. All right. So first thing we're going to go over is today we're going to talk about stereochemistry. Right. First thing we're going to talk about, stereochemistry involves working with things called stereoisomers. The other isomer that we hopefully remember are what? Anybody remember? Constitutional isomers. Right. Constitutional isomers, first off, both of these share one thing in common, the same chemical formula. So constitutional isomers have the same formula. Stereoisomers share the same formula. The only difference is constitutional isomers have different structures, or they'll connect differently. Something like this we will remember way back when. These two structures right here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. These two structures right here are constitutional isomers of each other. Same number of hydrogen, same DI, different connectivity. When we talk about stereoisomers, though, they all have the same chemical formula, same connectivity, but different orientation in 3D space. I'm about to draw an example of that. I know it's a lot of big words, but so let's go look at that. So here's an example of that. So we have yeah, Alex. All right, so looking at these two structures right here, first off, same chemical formula, 1, 2, 3, 4 carbons. Each of them have 4 carbons. Each of them has bromines connected to carbon number 2. But the thing is, in 3D space, they're connected differently. One's going to the wedge forward and one's going to the back. So these two are actually stereoisomers of each other. Anyone lost, confused on that idea? It's just all about, in other words, this chapter is all about wedges and dashes. Same connectivity, different orientation in space. And that's stereoisomer. When we talk about stereoisomers, we usually refer to things that have chiral centers. And chiral centers are chiral carbons. You can see chiral things. Chiral things are usually sp3 carbons, so carbons that don't have double bonds on them. And there are 4 unique substituents on it. So sp3 carbons. We're usually talking about carbons. sp3 carbons and 4 unique substituents. Also, on a quick note, please let me know if I'm not on this screen, because I'm going to be looking over at this laptop repeatedly. Right. So I'm going to draw a couple pictures on here, and you tell me where the chiral carbons are, or if we have any to begin with. Got it? All right, so let's try that. So we have three structures right here. Where are the chiral carbons, if there are any? So figure out both. The way we do that is we label chiral carbons with asterisks or # stars, whatever it depends when you use. So in this case, we have usually carbons with 2 hydrogens on it. We can just ignore. So this is CH3. We can ignore that. This is CH2. We're gonna ignore that. CH3. We're gonna ignore that. This is a CH carbon, implicit hydrogen, attached to a methyl, attached to an ethyl, and attached to a bromine. Bless you. Is that 4 unique things on there? Yeah, so chiral carbon. We're not even labeling it yet. We're just saying, hey, we found one. Next step. Is there a chiral carbon here? All because someone draw wedges and dashes on a picture does not mean it's chiral. Right? OH, hydrogen, 2 methyls. So this is not chiral. How about this one? This one is chiral. Usually in ring structures, if we have at least 1 substituent on there, or at least 2 substituents, yes.
Why isn't the second one chiral?
4 unique things on there.
Oh, okay.
In this case, how many things do we have on there? 3. 2 methyls, or it's just 1 group. 1 hydrogen and 1 OH, alcohol. Yep. Right here is right here, and right here, both of these are chiral. So there's hydrogens implicitly drawn here. And these chains connect differently than the other side. So we have chiral carbon. Anyone lost, confused on at least identifying chiral carbons? The other quick, fun way to do chiral carbons is if you have fused rings. And I think we've seen some pictures of this, and you've hopefully done some of this in your module. Anytime you have a corner of a fused ring, it's chiral. As long as there's no double bond there. Right? Whatever you do not draw this picture just yet if you're following on. Give me a minute to at least. So, like I said earlier, hopefully everyone can see this on the screen. Oops, wrong way. Put an asterisk by each chiral carbon, keeping in mind that every corner will be chiral as long as there are no double bonds located there. There's also in here a chiral carbon that isn't a corner. Right? As everyone works on that, this is one of the few things you can actually not use science to do. Just as long as you can picture geometry. Right? So let's look at this. I'm going to do this real quick. Just bear with me, okay? I don't remember what my picture looks like. I'm just going to look at it and go chiral, chiral, chiral. That's it. So we have a chiral carbon here, chiral carbon here, and a chiral carbon here. Because it's a corner of a ring, and there's no double bonds. Done. This is just this is not a corner, it's just a normal substituent with 4 things on it. Questions? Yeah, what's up?
Okay, so let's say we had like 2 carbons.
And we do.
Would they still be chiral?
This is chiral and this is chiral.
Even though like no matter like we can go around just do like
let's see, hold on. In this case, it's same this way, same this way. In this case, no, you're right. And for usually in most situations, there's going to be some sort of anything if we add anything to either side, it's going to make them different. But in this situation here, as is, no, we're going to say there is no chiral center in this one. We have to say yeah, so in this case there is none in this example right here. So you're right. So your questions. But next example here, because there are unevenly drawn structures, we can say that there are chiral centers there. This one right here? This one? This one? Okay, so we have a hydrogen here, so that's one thing. We have a carbon that's double bonded to another carbon here, that's number 2 thing. We have a carbon that's connected to a carbon that's connected to a double bond here. And if you go this way, it goes. If you drew a long chain out, you'll see a difference. Any questions on at least identifying chiral centers on a ring? We'll talk about symmetry. We'll talk about symmetry later, and when we start talking about meso and achiral things. Yes.
So but once you see like the first chiral center at the top, so your point, how they'll say you highlight what the chiral center is to add. So we stop at the as you're going down, we'll stop at that carbon, and then for this one you keep going until you get to the double bond, and for that one you keep going until you get to the double bond. Like which one have higher priority?
If you're talking about priority, yeah. And the difference. You'll see that there's a difference that just keep going that way, yeah. And that's always fine, yes. For this part right here? So for this chiral center, we have an OH, a bromine. We have a carbon here. These two carbons are the same, right? These are CH and CH right here. But this is different because this is a C double bond C and a C double bond C. So you'll see as you go out, it sort of progressively changes. It might be the same at this point, but then when you get to this point, they're the same. So you can keep, as long as usually 3 or 4 carbons out, if we don't go further than that, usually more than 4, you'll see a difference. Any questions on identifying, identifying chiral centers and chiral carbons? All right, so is everyone ready to do enantiomers, diastereomers, all the stuff that probably confuses everyone during the thing? All right, so let's do that. Before we do that, we have to learn how to do R and S. And usually I'm skipping a lot of things in between, but sometimes it makes more sense. R and S. R goes which way? Clockwise. S goes, and it's okay if you have to spin your finger to go which way is what, because I still do that too when I'm trying to figure out clockwise and counterclockwise. Like, but when I do it on this, when I'm doing it in front of you here, remember my clockwise is your counter and your counter is my clockwise. All right, so don't look at me when I'm trying to figure it out when I'm doing it up here. All right, so let's go and do clockwise, counterclockwise, and labeling priority. Labeling priority all has to deal with atomic number. So the higher the atomic number, or the larger the atomic number, the higher the priority. When doing any of this, I recommend when drawing your dashes and your wedges to always keep your wedges and your dashes next to each other. All right. So in other words, you see how this dash and this wedge are right next to each other here? If you can, make sure they're next to each other. It's going to be a little weird when you try to draw a picture that looks like this. How that, sometimes it kind of, it doesn't always work out mentally in actual model kit way when you draw the wedges too far away from your dashes. All right, so let's go ahead and do the priority for each one of this. So first we locate the chiral carbon. Our chiral carbon is right here, right? So step 1, find chiral carbon. I'm going to make sure I'm on the screen. Find chiral carbon. Yeah, what's up? No, as long as they're next to each other. So if you have to draw in your hydrogens, keep it right next to each other. Step 2. So here's your chiral carbon. Everyone's going to agree with that? Step 2, label priority. So when we label priority, we're looking at what's immediately connected to the chiral carbon. So what's immediately connected to this chiral carbon? We have a bromine, we have a hydrogen, we have an oxygen, and we have a carbon. Which one has the largest atomic number? Bromine, so we're going to give that one number 1. Who's going to get number 2 in our case then? Number 3? And number 4? Hydrogen. Is everyone okay with that? What question? Okay, we're about to get to that. So step 2 is label priority. Step 3, you have to swap the, well, depending on which teacher you had, Dr. DiMaggio does it slightly a little different, which is totally fine. For most everyone else, we always want our number 4, I'm not going to say hydrogen, but whatever priority group number 4 to be on the dash. What? Dash. So, 4 needs to be on dash. So we're going to have to do, if it's not already on the dash, we're going to have to do 2 swaps. Right? Is 4 on the dash yet? In that situation? No, right? So first thing we want to do is get 4 to our dash. So we're going to swap 1 and 4. So now our 4 is going to be here, and our 1 is going to be here. Usually when you're doing this, I recommend doing it in pencil because you can always erase it. Right now I'm doing it. I don't want to scratch it out right now. And which other 2 are going to swap in our case? 2 and 3. Why not? 2 and 3. So we're going to have 3 here and 4 here. Cover up your number 4. Which way is this thing rotating? Clockwise, right? Or let me. So I know it's too many numbers. That's why it's easier. Hey, so give me a quick minute. Hey. Oh, so I saw. Whoops, I apologize for that. So hold on. I saw 1 and 4. So it should be 2 up here, right? Thank you for that. Sorry. I'm gonna go ahead and so everyone. I'm gonna scratch out the numbers real quick. No, we'll scratch them all out. We'll scratch them all out. So, okay. So this was 2. So 2 goes up here now, and 3 goes here now. So that okay. No more confusion about what number goes where. All right. Cover number 4 up. Which way is this thing? Which way does you have to rotate this thing? Counterclockwise. If it's going counterclockwise, this is S. Right? Any questions on labeling chiral centers? Yes.
Okay, so like even if before it's like in between, you still just cover it up and just go whatever way.
The idea is you want to ignore number 4.
Okay.
Yeah, because you don't want to accidentally count 4 when trying to rotate this thing. Yeah. 1, 2, 3. Yes.
Do these steps work when it's in a ring?
Yeah, it works for all. This is the basic step for all. I'm about to go to each example for different ways to draw the structures now. But is everyone okay with labeling, identifying, and rotating? All right, now we're going to go over all the tricks on how to figure out what picture does what. All right, let's go one at a time. First things first is, let's go, because I know this is a review, so hopefully y'all at least started something. So first thing we're going to do is ring. People have trouble doing this method that I'm going to show you that I use works for all rings. Cyclohexane, cyclopropane, cyclobutane, any ring. So let me show you. I'm going to show you with cyclohexane. It's a little. This is going to be a little different than what y'all seen in the review session on the video. It's actually a lot different. So here is cyclohexane. So for those who are here during this review, this right here is cyclopropane with your model kit, something we tell y'all to try to use. All substituents on your ring will always be going towards you. Everything else on the side will be going away from you. So anything that's going top and down was always wedge. Everything on the side will always be dash. You can think about this as, we'll probably talk in a minute, you can think about this as opposite fissure. When we will do fissure projection, you've seen this before. Fissure projection is here, right? And then for fissure projections, we do the bow tie method. Right? So normally that's what we normally do for fissure projections. But unlike fissure projections, when we do rings, we do the exact opposite. Top and down are wedges, left and right are dashes. So let's go ahead and do, so first thing, just like before, let's go ahead and identify where our chiral carbons are. So where is your you'll see how I draw it in a minute. So here's a chiral carbon and here's a chiral carbon. Everyone okay with that? At the very least, at least that much, right? So chiral carbon, asterisk, and asterisk. So we're going to do opposite fissure. Opposite fissure says that we do wedges go top and down, and everything else is dashes. Right? With this method, you guys, questions?
So whatever's in the ring is always going to be opposite.
It's easier to think that way. Because when you actually make the model kit, you'll see that any substituent you put on there will always be going towards you. So I usually draw the opposite fissure, and then I put the priority number here instead. So chlorine is right here. So who's number one on this chiral carbon? Who's the number one priority? Chlorine. So we're going to put 1 here, because that's where chlorine's at. Which one is number 2 then? Here, right? So we're gonna go over. We're gonna talk about how that's number 2 in a minute. Our number 3 is this one back here, and our hydrogen is number 4. Do your whole 2 swap method to get 4 to be a dash, then figure out your chiral centers. Right. This back carbon right here. We're gonna go over why it is in a minute. You're looking directly at. Imagine this is your compound. You're looking directly at it like this way when you're doing opposite fissure. Right. Oop, no, that's not good.
Does it matter which dash you put the 4?
You kind of want to get used to saying wherever it's up stays, wherever up stays up. What do you mean 4? I'm confused about that. Say again.
So you said get the 4 to the dash because there's 2 dashes.
It doesn't matter which one.
Okay.
It doesn't matter which one. All right, so let's look at this for a minute. Yes. It doesn't matter which one, as long as you get 4 to a dash. So you can swap 4 with 2 or 4 with 3, still get you it should still get you the same answer, as long as you swap 2 different groups. Second. When I do fissure, I use left and right on my wedges, like this. Yeah. People might do some people might do fissure a little bit differently where you could do that. It's usually give you the same answer. That's just to give you the same answer, yes. So let's go ahead and look at this. Why is this number 3 and why is this number 2? So let's go and let's look at why. So this is chlorine. Chlorine has priority number 1, right? Because it has a larger atomic number. When moving across here, we have a carbon here and a carbon here. So they are tied. Everyone sees that they're tied? When you have things that are tied, I usually write the thing that is tied down and underline it. So we have a carbon here, right? That's right here. What's connected to this? What's directly bonded to this carbon right here? So we have a hydrogen, a chlorine, and a C. Usually I put it in priority order. So it'll be Cl, C, and then an H. Because there's like on this carbon, there's a chlorine attached to it, a carbon attached to it, and a hydrogen attached to it. Whatever I underline is what I'm pointing at right now. So let's go over here now. We're looking at this carbon. So write it down, underline it. Then ask myself, or y'all, what's directly connected to this carbon? Okay, so you say 2 hydrogens in a carbon, but put in order. Carbon and 2 hydrogens. You put it in priority order because we're going to compare things in priority order. So let's look at each of these carbons. Both of them are the same, correct? So you have a carbon here and a chlorine here. These two are different. Which one has higher priority? Chlorine. That's why this way is number 2. And that's why this was number 3. And that's what happens when you have tied things. We're going to do more rings in a bit. But that's in gist of how you figure out things that are tied. So what did everyone get for this structure here? R or S? Did everyone get S? Yeah, so I'm just going to take your word on it. S. Right, this has to be S2 then, but we'll talk about. Any questions on figuring out this chiral carbon here?
Wait, did you have like something else?
You always have to swap something. You always have to swap it so your 4 is on a. Yes, always. At least for y'all's situation for right now. Later on you can do it without doing that, but for now please do that.
So the one on the right is S also.
It will be.
Is it always the same? Or does it?
It's a trick that you'll see.
Okay.
When they're
If you swap it, it'll be R.
okay, so let's swap it. So 4, I'm going to swap 4 with 2. So I'm going to redraw. I usually always redraw my picture. 4 with 2, so 2 goes here, 4 goes here. And we're going to swap 1 with 3.
Oh, you got to swap twice.
A rule is always swap twice. Although it depends what teacher you're talking to, but swap twice is what y'all should be doing. 1, 2, 3, S. Go ahead, if you haven't done it yet, go ahead and do this chiral center here using the exact same method. I highly recommend, because I know I do the same thing too. After you try to label this chiral center, what do you have on your paper? A lot of pencil markings, right? If you are very certain that you are okay with this being S, I really recommend just erasing it. Erasing all your numbering. And just doing it again here. Because at the end of the day, your paper probably looks like this. 1, 2, 4, 2, 1, 3, 4, 7, right? So you see how it just looks like an odd mess with a whole bunch of numbers on there. When you finish a chiral center, I recommend erasing it and work on the next one. Because if too many numbers, you might pick the wrong number for your rotation. You should, at the end of the day, got S on this chiral center. Did everyone else get S? Or who's anyone working on it right now before I move on to the next one? Yes.
I don't like that, but when you were looking at it earlier, it was like this one has to be S2. Like you said,
Okay, so let me show you. Let me show you how to figure out something without actually trying. Right? But you need to figure out one first, right? If this guy here is, so I'm gonna show you 2 pictures, and we're gonna talk about enantiomers in a minute. If this is S, and this is the exact opposite of it, right? Are these mirror images of each other? If I put a mirror down this middle, would they be mirrors? No, right? So that means they should have the same chiral center. Because so let's look at this. Let's look at this for a minute. Let's look at this. Let's look at this. Can everyone see the structure right here? Yeah. So I'm going to go ahead and label the chiral center here. So this is R. This is R. I'm going to tell you this is R. Right. This is R right here. So if you take the time and do the same thing we did a minute ago, you figure that's just R. Because we have 2 chiral centers in a mirror plane, this should be the opposite on this side, so this should be F. They actually, this compound's meso. But we're gonna go over what those words in a minute later. But that's it. If you know the definition, knowing the definitions and knowing how to use them gives you the small tricks. So I really can't tell you here's what will happen. But if you look at it, that's what happens next to each other. Yes. Oh yeah, sure. This one. Yeah. Yeah. Yes.
So like the chlorine and hydrogen, like where is the recipe?
Yeah.
Okay.
So let's go ahead. So we can do this. Let's go ahead and label this chiral center here. So 4 is hydrogen. Everyone's gonna agree on that. 1 is chlorine. Everyone's gonna agree on that. Which one of these will be our number 2? This one right here, correct? So the one to the left will be our number 2, and the one to our right will be our number 3. Again, is our 4 on a dash? So we're gonna have to do 2 swap, and once you do 2 swap, hopefully you should get F. Right, I'm actually running out of space here, so I really can't do that. Yes.
Do we always have to do 2 swaps?
No. If you understand how to do 1 swap, and you were taught how to do 1 swap, and you're okay with 1 swap, you can also do 1 swap. But for those who can't, I recommend doing 2 swap. 1 swap. Okay, so for those who are questioning what 1 swap is, if you swapped it once, you have to remember that your answer that you come up with is opposite. People forget to. That's how I do it, but that's because I done 2 swap enough to understand 1 swap is okay. Right. That's why 2 swap is 100% do 2 swaps, so you won't, whatever you write down is your final box answer if you forget to tell them this is your answer. Yes?
You said if it's a mirror image, they don't have the same chiral center?
They don't have the same chiral center.
Okay.
If they are the mirror image of each other, they don't have the same chiral center. Right. So everyone okay with this? So let's talk about enantiomers, diastereomers, chiral, achiral, meso, etc. like that. Right. Sorry, if something's chiral or achiral. Right, so. All right, so let's go. So let's go with this. Let's say you figure out let's say your compound only has one chiral carbon, and you found out it's R, and you did the other one, and you found out it was S. These two are mirror images of each other. Right? R is the opposite of S. If they're mirror images of each other, they are enantiomers. By definition, that's what an enantiomer is. We're going to go by a mirror image of the other guy. So these are enantiomers of each other. Anytime you have a mirror image of something, it's always an enantiomer. What if you did, let's say you did your stereochemistry for your 2 structures, and both of them, I don't want you to memorize this, it's more of an understanding. And you found out that both of them are R. Most likely these 2 compounds are the same, right? They're not mirror images of each other. They're probably most likely the same thing, just rotated differently. Usually if they share the same connectivity and they share the same chiral center, and they're pretty much the same compound, just drawn backwards probably, right? Let's say you did a Fisher projection. We'll do one of these in a minute. Let's say you did a Fisher projection and you did the chiral center and you found this one was R and this one was R. You found this one was S and this one was S. Are these 2 mirror images of each other? If I put a mirror in the middle, does this side mirror this guy and this side mirror this guy? When we say mirror, we mean opposite. Not the same. When we say mirror, it's not the same thing. So these 2 are opposite of each other, right? So these 2 are enantiomers of each other. Whenever you have a mirror of the other guy, you might have an enantiomer. We actually do have an enantiomer. We're going to go with the might bit in a minute. In the same ring? No, okay, no, we'll get to that one in a minute. When talking about enantiomers and diastereomers, when using that word to describe 2 things, like these 2 are enantiomers of each other. these two will be diastereomers of each other. When you use the word meso and meso, we're describing this one compound by itself. Like, is this compound meso? Is this compound meso? Right? So when we're comparing two things together, we're talking about enantiomers and diastereomers. Yes?
For the, what are you comparing? So, you have to find the power center, the priority for the first time, and the top. So are you comparing the first two points or?
Yes. If they mirror each other, yes. Are these two compounds here enantiomers of each other? So if you have more than one chiral centers and they're not mirror images, they're diastereomers. So when there are two or more chiral centers and they're not mirror images, they're diastereomers. These two are opposite of each other, so that's great. These two aren't opposite of each other. So these two compounds are not mirror images of each other. These two here are diastereomers. So by definition, diastereomers are two or more chiral centers. So it can have 3, 4, or 5. And they're not mirror images. The other definition of diastereomer is if you have something that's cis and compared to the same thing that is trans. So this diastereomers can also be used to describe double bond things. One thing cis, the other one trans, they're diastereomers. That's just another definition of it as well. There you go. There you go. So, all because these two, one of this is trans and the other one is cis. All because we see cis and trans doesn't mean we automatically go, yeah, diastereomers. We have to make sure they have the same chemical formula and same connectivity, right? These double bonds are in the different spots. I might have drew one too many carbons in one of the pictures, but you get the general idea. If it's in the same area and they're cis and trans, we can say that they're diastereomers. See how this double bond starts at carbon 3 and this double bond starts at carbon 2. These two are actually structural isomers of each other. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, done. Okay. Fix that problem real quick. Okay. These are structural or constitutional isomers, same thing, and not diastereomers. Right. All because we see cis and trans doesn't mean we can automatically jump to that conclusion. It has to be cis and trans, same connectivity, different orientation. Conformational isomers, you still see them. When we say conformational isomers, we're talking about things that are Newman projection versus, so staggered versus eclipse. Those are conformational isomers. You still, again, organic chemistry, they'll always ask something that you learned from chapter 1. So you always still need to remember that. I'm not sure if they ask it, depending on which real instructor you have. Any questions on enantiomers or diastereomers?
So those last two aren't diastereomers?
These two aren't. These two are not diastereomers of each other.
They're just not.
They're constitutional isomers.
Okay.
Yeah. So the double bonds are in a different spot. That's all. Yeah. Yes.
I have a question. When doing like the chirality thing with that
Spatial projection? Yeah, spatial projection.
How do you know what's the dash and wedge on there?
Wow, you're just leading up to every next topic. Okay, let's go do that. All right, so let's do Fisher. We're gonna go back to enantiomers and diastereomers too as we do these. So after this point, it's just I'm gonna draw a picture. We're gonna try to draw it. If you don't get it, we're gonna keep drawing more pictures. Everyone okay with that? And this is chapter in a nutshell at this point. You already know what the words. Oh yeah, we gotta go over meso. Oh, whoops. That's not. Yeah, so it follows the same idea. when things are, so first off, we need to talk about things with plane of symmetry. When something has a plane of symmetry, that means you can draw a line down the middle of the compound, and you have two halves that are the same. Yeah, I'm just going to take everything that you said. Right? So let's look at this picture right here. We can draw a mirror down the middle here, and it reflects both sides. So this structure has a plane of symmetry. Everyone okay with that? If you have actually a mirror, I mean, most people don't have it anymore. You can actually place it in the middle, and you get the same picture cut in half. Actually reflected on the other picture. So that's a plane of symmetry. When something is meso, so two requirements for something to be meso. First off, it needs to have at least 2 chiral centers. And plane of symmetry. So always check for the first one first, then go on to the next one. Meso compounds are we'll get to it in a minute. So let's figure out which one's meso first. So let's look at both of these structures here. They both have a plane of symmetry. Is everyone okay with that? Do both of them have chiral carbons? First off, this one does. It has 2. It has one here, and it has this one here. Everyone okay with that? These 2 here are not chiral carbons. This here and this here. They are not chiral carbons. Can anyone tell me why they feel it's? Because both, no matter which way you go, it comes the exact same thing. So it's CH2. So it's not really 4 unique things on that carbon. So in this case, we do have plane of symmetry, but no 2 chiral carbons. So in this case, this compound right here, this one is meso, and this one is not. Everyone okay with that? Meso compounds always need to have 2 chiral carbons and a plane of symmetry. And because we know there's a mirror plane in the middle, whatever chiral center I find here, the opposite should be here. That's why I was able to do so quick, because I knew looking at the picture it was meso. You're like, oh, figure out one, figure out the other. If it's a mirror, right? If this was R, this one would be. That's the idea. Yeah. So if you know it's meso by looking at it, if you solve for one of them, you can automatically fill in the other. Is everyone okay with that? Meso compounds are achiral. When something's achiral, that means it's optically inactive. So yeah, here's one word that you don't know, and here's another word that you don't know that follows right behind it. Right? Optically inactive. The way we can think about I can't spell inactive. When we talk about optically inactive things, it means that the R's, you can think about it as the R's cancels out the S. Or something's optically inactive, the R's cancels out the S. So if you have 50% R and 50% S, optically inactive. If you have a compound that's meso, since they're 1 R and 1 S, that's optically inactive. Right. So all meso compounds are optically inactive or achiral.
Can you explain why the second one is not?
So we have a plane of symmetry, but we don't have 2 chiral centers. So this is a carbon that could look chiral. So we have an OH, that's 1 group. We have a hydrogen, that's 2 groups. But you have, these are both CH2s, right? These are both CH2s. And they're all connected to this whatnot. So they're not this is not unique compared to that guy. So there's no chirality there. That's why we can't say it's meso. Yeah. Questions about that? Any questions about meso compounds or achirality? Which one? This one?
Yeah.
Remember, when we're using when we're using the term enantiomer and diastereomer, we're using to compare 2 different things. It's just one cell. I can say this compound is meso, but if I draw a different compound next to it, maybe then I can compare if they're enantiomers or diastereomers.
Okay.
Yeah, so that's the two different words used for two different reasons. Yeah, that's a better way of looking at it.
For this next image that's not, if it was on the far left, it was coming down for like this, would that be considered, would it be?
So if we moved it one closer, yes, it would be. It was. You would still be. It would be chiro and it would be meso. Yeah. In optical inactivity. To be chiro means you are more. When you're chiro, that means you either favor R or S. When we talk about R and S, it's how much they bend light. So when something is a lot more R, it bends light in a certain degree. If it's more S, it bends light in the opposite degree. That's the biggest separation in terms of how we figure out something is what, other than talking about melting point and chemical properties. Right. Any other questions on that? Oh no, I'll go more into detail on how I can what that means, but without doing the actual math problems. All right. Let's go and do Fisher projections now. Right. Oh, can someone give me the time? Thank you. Okay. All right, let's do Fisher projections. I'm going to show you how to start one. Then I'm going to give you a problem so we can work on. Whenever you have a Fisher projection, I'm going to make sure I'm on the monitor. Okay. Whenever you have a Fisher projection, we have something that looks like that. The way you do Fisher projections, or the way, rather, I'm going to say this, the way I do Fisher projections is I do what we call bow tie. We just mentioned it a little earlier. Anything that goes left and right, we make wedges. Anything top and down, we make dashes. And that's it. What? Wedges are we use wedges as top down when we're talking about rings. Yeah, there's no real term for that, but that's what I call it. Yeah. There are different ways we can. If you want to look at a different way how to do rings, watch the first video on the review session, and it shows it a little different way. All right. So that's how we set up a. Let's not figure out the chirality of this guy first. Let's go actually try this one. All right, let's figure out the chirality of this structure here. Oh, someone please remind me that we need to go over naming these things and how to draw these things as well. Okay, there's usually I forget to do those. I would try to name this, but I don't think y'all know most of these functional groups yet. First thing you need to do is what? Locate chiral centers. How many chiral centers are there here? 2. This first one here and this one here. This is, huh? Yes. So these are 2 chiral centers here. This is not a chiral center because there's 2 hydrogens on there. Is everyone okay with that? Okay, now figure out the chirality of either both of these. So go ahead and pause the video now and wait for it, then work on the problem, then click replay, then we go ahead and do it again. Because I'm gonna edit these videos, so I need to give myself notice. The annoying part is I'm gonna have to watch all my videos twice. All right, so let's go ahead and do this. Everyone okay? Anyone working on it right now? Okay, go ahead and just try. All of these, it's best that you actually do on your own. First thing you need to do after you do that is set up the bow tie. And then figure out, so let's go and start labeling things. At the very least, so that we're on the same page, at least the same page. For the very first carbon, which one are we going to give number 1 to? Bromine. Is everyone okay with that? Bromine. Number 2 goes to oxygen. Number 3 goes to, because both of these are carbons, right? Carbon here and a carbon here. This carbon is connected to a oxygen. Actually, ooh, I apologize. Let me go ahead and just put. Thank you for that. Yes, should be one more. It should be one more. It should be one more hydrogen on there. It doesn't change. It doesn't change the answer overall. 1, 2, 3. Oh, it should be 2. Should be 2. Should be 2. C2OH. Should be C2. Because remember, all carbon needs 4 things on it. Okay, so let's look at this. So this carbon here is connected to this carbon. So we're going to write this down right here. Underline it. What's connected to this carbon? Oxygen and 2 hydrogens. Oh, sorry. Yeah, sorry. There you go. Right. If we look at this carbon here, we have a carbon. What's connected to it? Another carbon and 2 hydrogens. So which one has higher priority? Top one. And that's how we do that. Yes. Yes? This is the, remember this is how we write aldehydes. Not this meant to be alcohol. Yes. COH is alcohol. CHO is aldehyde. And you will see that, and CO2H is carboxylic acid. Yeah, and or they will you'll see it written these ways when it's written as a Fisher projection. So this one is number 3, and this one is number 4. Again, before we do anything, we need to turn this into bow tie, right? It's already Fisher, so we got to turn this into a bow tie. The H is not the one with the 2. It's the oxygen that has the 2. Yeah. 2, we put in priority order. Yeah. Wait, is anyone confused on that? I want to make sure. I didn't mean to say it that way, but anyone? Okay. So is our 4 on a wedge already or a dash? Dash. So do we have to do a swap? No. So which way is this rotating? R. This is rotating clockwise. Anyone? Huh? So 1, 2, 3, 1, 2, 3. So it's spinning this way. So it's going clockwise. Is 4 on a wedge or a dash? Yeah. You'll see. We'll go ahead and do that. So let's go ahead and do this chiral carbon right here. Which one is number 1 in our first? Bromine. Same thing. So now let's figure out which one is 3 and 4 now. So it says both of these are carbons. We underline it first. What's bonded to this carbon here? H, H. So what order, how would you put it in order though? Yeah, C, H, H. So we just did this carbon right here. Now let's go and do this carbon right here. So we have a carbon, underline it. We know this is C double bond O, H. So when it's double bonded, we write it as if it's bonded to it, to 2 of them. So it'll be C, 1 oxygen, another oxygen, and a hydrogen. When making the list, you put it in priority order. So which one has higher priority? This one or this one? The bottom one does. So this one is number 3, and this is one number 4. And again, bow tie everything. Is our 4 already on a dash or a wedge? It's on a dash already, so we don't have to swap anything. So which way is this thing rotating?
Clockwise.
Still clockwise. This is also R. The structure is R. So go ahead and count for yourself and rotate it to make sure it rotates. Hopefully, and check myself to make sure it's rotating R.
Peter, can you do one where you have to like flip things?
Oh yeah, sure. Yeah, okay, we do that. Aldehyde. This is short way of writing aldehyde. Yeah. This is how so looking at this short way of writing. It's what? It's a short way of writing carboxylic acid. It's the same idea. It's like it still expects you to remember those shorthands. But that's how we actually write it in these structures. So what? Yeah, sure, okay, yeah. Oh, we're gonna start naming, but not this one. Let's go ahead and start naming and then drawing, so that way if anyone has to leave or eat dinner, you can just, majority of what we did is already covered. The only other thing that we need to talk about is you also have to keep in mind you also can rotate these structures on a single bond. Right? So if you have to bring your model kit, bring your model kit. You have to open your model kits and start using it, do that as well. But some structures can be rotated around its Newman projection to make it look like the other picture. It's just not drawn that way. And I might be able to draw one in a bit. But let's go ahead and just first name and then draw. Name this, okay, before you start, name this compound here. Do not worry about the wedges or dashes. Just name them just the way you know how to name things. Naming doesn't change. Naming, the way you used to name things still has not changed. Just name it like normal. Step 1, find parent. I'm hearing a lot of wrong answers out loud. First, first find longest parent chain.
Right.
Did everyone follow that?
Yeah.
Oh, thank you. Okay. All right, first off, what is the longest parent chain did everyone get? 5. 1, 2, 3, 4, 5. So that is a pentane. And everyone okay with that? I'm gonna go ahead and just circle the parent chain. I tell y'all to do this all the time, but yeah, I still don't. Where your substituents at? Which number? 2 and 3, right? So we have 2 bromo, 3 methyl. I'm gonna run out of space, but is everyone okay with just naming like normal? Next thing, we need to figure out where our chiral centers are. At which carbons? Carbon number 2 and carbon number 3. So let's figure out the chiral center around carbon number 2 first. So what is it on carbon 2? Is it R or S? So whenever you're comfortable telling someone, give me what they think the chiral center is. It's actually R. Or you can actually do it yourself. Hydrogen isn't in here, so first thing we need to do is include the hydrogens, correct? When you draw your hydrogens, like we said earlier, when the dash needs to be next to the wedge to it makes it easier for drawing and picturing. So hydrogen's right here. So this is number 1, this is number 2, this is number 3. 4 is already on the dash, rotates clockwise, R. I know we did it a little fast, but number 1, number 2, number 3, and number 4. Rotates clockwise. So on carbon number 2, it's an R. Everyone okay with that? Now do the same thing for carbon number 3. So take your time and try to do this one on your own. First, label your priority groups. Make sure your 4 is on a dash. You have to swap it, but do it twice. Yeah, sure, yeah. Yeah. Hold on, let's see. Is it? No, no, it's not. It's S. It's very S. It's very S. Did everyone get S?
Yes.
Or for those who are still working on it, go and try finish, but you should have gotten or will get S. Yes. Say that question, the last part of the question again.
So like, if you said it doesn't matter if one right? But if we have to fill it in ourselves, couldn't that affect, like, if the dash on the left, could it affect the
as long as you put them next to each other, it should be fine. Should be fine. But just check anyway. From the ones I'm picturing right now, it should be fine.
So if we just stick with that, they come last.
If you do the Newman projection thing where it goes wedges are right, dashes are left, it should still be fine too. Yeah, that should be fine as well. That's 1. Yes. 2. And this is 3. And then 4 is not on there. Yeah. So for the final name of the structure, we have to say where each of these chiral carbons are. So carbon number 2 is an R, and carbon number 3 is an S. You would put this in front of here, but I ran out of space. Any questions on naming structures? So you name the structures just like normal. Find your chiral centers. Label your chiral centers. If it's only one chiral center, you don't have to say where it's at. Only cis and trans only works for double bonds and rings. Do we have either in this case? Yeah. But you still have to remember. Oh, yeah, they would do this for you. Make sure you still remember to put cis and trans for structures for rings and double bonds. Hmm? Or double bond. She just asked that. All right. So let's everyone ready to let's go ahead and do the name to structure now. Right. I'm going to turn the page because it's going to be hard. Right. Since everyone looks like they just want to just do practice, so let's go do that. One, two, difluoro, cyclo, pentane. Difluoro. Carbon 1 has an S, and carbon 2, might as well be an R.
So that's how you just put the chirality just right in front.
Yes. So let's go ahead and draw. Let me show you how I draw name from name to structure. So first thing you do is you draw this as if it was normal. Ignore the whole chiral center thing. So let's go and do that. So what's our main parent? A what? Cyclo what? Cyclopentane. So it's just a big pentagon. Everyone okay with that? And more or less. So where's our fluorine on carbons? Which one? 1 and 2. 1 and 2. Everyone okay with that? The next thing I do is where the chiral centers are, I give them all wedges. It doesn't matter what it is. I don't care if it's R or S based on the name. Because on carbon 1, I'm going to give it a wedge. And on carbon 2, I'm going to give this one a wedge as well. Yes. Now, at each of the wedges, I figure out what the chirality is. What is the chirality of this here? Is it R or S? Go ahead and try to figure that.
The first one or the second?
The first, this one right here, the first one. What did you get?
S. Wait, you said the chirality?
Is it R or S?
It's S.
Please label your papers with the priority group numbering. It's R. It's very R.
Oh, it's R.
Okay, so hydrogen's not drawn in there, so it's going to go to the back, right? It's already gone to the back, so we're not swapping anything. This is number 1, this is number 2, and this is number 3. So this is R. Do we want carbon 1 to be an R? No, right? We want it to be a S, according to the name. So instead of a wedge here, we should put a, just turn it to a dash. If with your pencil, you would erase it and go, oh, now it's a dash now. And it automatically switched to the opposite side. Now it's an S. What?
Okay, can you explain the whole thing? That's why I needed like counting situation to make it an R.
This is 1, this is 2, this is 3.
Okay, so why can you go the other way? 1, 2, 3.
This carbon is connected to a fluorine. This carbon is connected to another carbon and a whole bunch of hydrogens. So this one has this carbon right here has a higher priority than this one. Okay, I'm gonna list it out. These two carbons are the same, correct? So I'm gonna write carbon and underline it. What's connected to this carbon? You tell me. So carbon and 2 hydrogens, correct? What's connected to this carbon?
A carbon, a hydrogen, a fluorine.
So fluorine, a carbon, and a hydrogen. Which one has higher priority?
At the bottom.
That's why this one is number 2. This is 1. This is number 3.
Is that just counting from that shop fluorine though?
Yes. This is just this chiral, talking about from this chiral carbon right here.
So when you count on the bottom fluorine?
No, go ahead.
If you count from the bottom chlorine, is that a chiral bond?
It is, but we're doing one chiral at a time.
Oh, okay.
Yeah, we're just doing one at a time. So we know that this is R, and we want it to S, we just turn it into a dash. So go ahead and figure out what's the chirality of this carbon right here. Is this R or S? What is it? It's S. What do we want it though? So we need to turn this one to a dash.
Like you could just be like 1 and 2.
Yeah, you could, it's swapped to the opposite side, right? Yeah, you could have done the same way as well. Yeah.
You can just count them the other way instead of kind of never mind.
No. You are it's flipped, so you can actually yeah, you're right. You could do that one. But in most situations, it's just in all of these pictures when going from name to structure, it's give it a wedge. You check the chirality. If it doesn't match what you want, turn to a dash. That's overall the same. But that trick where you know that the other one should be the same and flip it, that works as well. That works totally fine. Yeah, I understand what you want with that. Yeah. Any questions about going from name to structure? Your name, swap it. Keep it. Like if we wanted an R and it was an R with the wedge, it's fine. We did the first picture. That's the idea. No, R because that's the name of the structure. The first one's R. This first one, huh? This one. This one was S to begin with.
Yeah.
But we want carbon number 2 to be an R.
So the first one needs to be
It depends which one we call carbon 1 and which one carbon 2. I'm calling this one carbon 1, this one carbon 2. Yeah, this is where you're flipping thing actually. Yeah. It's all which one you want to call carbon 1 and carbon 2 because you're the ones putting your substituents on there. Any other questions? Any more practice problems or pictures that you need to be drawn or go through?
the official one. You have to like switch them.
Oh.
Just with 2 chiral centers.
Okay, I'll do that one.
Can you go more time about why you switched to dash?
Whenever it's not the chiral, okay, so not this picture in particular. Whenever you don't get the chiral center that you're looking for, turn your wedge to a dash. Let's go with that. That's overall. That's exactly what I also wanted to say for that part. So let's look at this picture versus this picture right here. So this is someone asked, what if I had to rotate my Fisher projection, right? So let's look at this. So. What are these structures? Are they the same? Are they constitutional isomers? Are they enantiomers? Or are they diastereomers?
They all have the same gravity.
So step 1, unless you're used to it already, first thing you want to do is label everything. Right. So let's go ahead and figure out each chiral center. There's one here. Whoops. Someone say 4 chiral centers? Oh yes, yeah, total, yes, yeah. Right, so let's figure out the chiral centers for each one of these. So we have one here, one here, one here, and one here. Is everyone okay with that? These two are the same. You just have to solve one of them. I made that a little easier for you. So there's only 3 chiral centers. There you go. So which one, so again, label priorities, turn to bow tie, and swap if you need to. Also, if you are given a Newman projection, these are more hints. So if you're given a Newman projection,
This kind of.
that's horsal, but it looks like you can see it's like a horsal as slightly related to Newman. You know, I like how y'all just correct me with these words because y'all know them now. So yes, it is sawhorse, right? You can always draw sawhorse pictures into Fisher projections as long as they're eclipsed. So if you have to rotate it to become eclipse, then you can draw, because they will never just give you straight up here. Here's a eclipse confirmation. That you can always first turn it eclipse if you're comfortable with that. Then you can draw it exactly like a Fisher projection, and then you can just do bow tie. These structures only look complicated unless you know how to just get to something that you're comfortable seeing. So did anyone give me the chiral centers for the bottom one? 1, 2, 1, 2, 3. So did y'all get? So did you get S? Did everyone else get S?
Mm-hmm.
For the is that the bot? Which one did you get? Sorry, which one did you get it for? This bottom one. So S here. So it's also S here. How about this chiral center up here? So again, I'm still gonna draw a bow tie. Also, if you have not yet, please before you leave, do me a solid and sign in. That's all I ever ask from y'all.
Thanks.
Oh yeah, and also doing well on your drills, but please sign in. Also, if you watch the videos on your own time and you find like the quality's bad or shaky, please let me know in person. So that way I can fix it for later or can adjust that as we go. Right. Yeah, I recorded that from my desks, and that was really random. I wasn't planning to do this. So I'll figure out better setting for that way. Thank you though. What is the chiral center? What did you get?
2, 3, 4. This is 3 because it's a VR.
So let's look at for this one. What did you get? 1, 2, 3. This one I got S.
Yeah.
Hydrogen's already in the back. So I got S on that, right? What is this one right here then? 1, 2, 3. Sorry, it's 4. Sorry, this is 4. This is 3. We have to flip and flop it. So which one is this one? S. Huh? They do, but it's just rotated differently. These two compounds are actually the same. Huh? Yeah, all S's. Well, if not, you can actually take if you take your model kit, you actually can rotate it to actually, if you rotate the top one, it's actually the same one, just off a little. Can I flip it?
Can you actually?
What? Wait, no. What's it? No, go ahead. What's the question?
Okay, when I say I put like the little top part together or something. With this be VR and then this be the
Make a Newman projection with your model kit. So you need 2 of those. Is there any further questions? Yes.
Right? Oh, right.
Is this really going to regular line?
Yes. That is. Yeah. Yeah. Let me start.
How do I rotate a piston? I'm gonna draw the second one real quick.
Oh, you still going?
No. Wait, what is it? Oh, how do I turn this off? The first thing you do is, when given any software, the first thing you need to do is turn it eclipse. So right now the figure is static. So it doesn't matter how eclipse you do it, as long as it's eclipse. So let's go ahead and let's keep the bromine going up. And let's turn this whole thing just a little so the hydrogen is also going up. So I'm going to draw it here. Yeah, let's go ahead. I need to rotate the back. So bromine here, going here, and methyl here. And we're going to rotate the back one. So hydrogen goes up. So let's take this. It's going up. Bromine goes over here now. And the other ones of your methyl goes over here. Is everyone okay with that? With how I rotate it? I just took the back. I took this back one and I just rotated it just a little to become close. Right now it's staggered. For those, there are different ways you can solve these problems. But this is how I use. This is how you so y'all can see how I do it.
And it doesn't matter which way you rotate the back.
As long as you get it eclipsed, that's all that matters. Because you can't turn it into a Fisher projection unless it's eclipsed.
Okay.
So now let's turn this into a Fisher projection. Yeah. So hydrogen's up here, bromine's down here. Like so, let's keep it like that. What's on the left hand side? OH. What's also on the left hand side over here? Methyl. OH is over here. CH3 over here. That can do S and R with both times. Doing R and S with this, you have to remember these are actually going towards you and these are going away from you. It's 3D structure, so it might not work out. The wedges and dashes aren't what you think are wedges and dashes, unless you do Fisher, which makes more sense.
And you'll still get the same answer.
You should. Yeah. As long as you put the right ones on the right carbon, you should be fine. This is how you go from solid force, staggered, solid force eclipse, to Fisher projection, then size and minus. I know it's a lot of work, but this is a guaranteed way to do it without overly stressing. Right. Any other questions?
Is that the whole master chapter pretty much?
Well, I skipped the whole enantiomer excess part.
I get that.
Was it in the video?
Oh no, I also said during the video that I also skipped it as well.
So every time
So this one was